Hi, this is lesson 8 in the use of JASP, and today we're going to cover the one sample t-test and talk about how to enter data directly into JASP. So, what we have been doing is, in our first lessons, is going to the 3 dots and then opening up data from the data library. If we have new data to enter ourselves, we can go to New Data, press on that, and then we can enter data straight in here. Now, the data that I'm going to enter comes from an example that I use in teaching undergraduate stats, and I ask them, how good of a driver are you? And I ask them to rate how good they are as a percentile ranking. Hence, if they're the worst driver in the world or on campus. So if you're the worst driver on campus, that would be a 1. If you're the best driver, it would be 99 or 100% if you're the very best driver. 50th percentile would be average, and they can choose any number from 1 to 100. And here is some examples of what I get from actual students. 93, here's a person thinking they're the best driver at 100, an 82, a 65, a 70, 42, 75, 62, 50, 52, 48, 48, 25, 85, 75, and another who's the best driver on campus. So that would be, that's the data that I got from one class, just choosing 16 at random from the class. So we want to go ahead and specify what kind of variable this is and name it. So I'm going to double click there and I'm going to write that this is driving ability on a percentile rankage basis. So that's the name I'm going to give it. I usually try to keep my names pretty short. I like my names to be within 8 characters. They can go longer, but I try to keep them within 8 characters. And here we're going to choose whether or not it's a nominal variable, ordinal, or a widely ranging continuous variable on a scale. And it is on a scale. It's not computed. We directly inputted it. We can go ahead and write a description of that if we want to for documentation purposes. Driving ability as a percentile ranking. When I'm done with that, I can hit this button over here, say that I want to apply the changes, and now I'm ready to rock and roll with my analysis. I'm going to go over to t-test, and on the classical side, go down to one sample t-test. I only have the one variable to study, so I'm going to go ahead and put that in as my variable. I'm going to go ahead and do a student t-test, and the hypothesis here is that people estimate their driving ability to be better than average. And average as a percentile ranking would be 50. So my hypothesis is that on average, the students are going to come in with an average rating that is above the 50th percentile, because if they were completely accurate in estimating their driving ability, they should come in right around 50, with some people saying I'm pretty bad as a driver, some people saying I'm pretty good, it should average out to 50. I don't think that's going to happen. I think they're going to overestimate that value. So I'm going to put that in. And I'm already getting results over here, which we'll talk about in a minute, but let's go ahead and specify that we want to get our parameter estimate. Where's that located? I want to see the effect size. I want my basic descriptives most importantly. Can also get some plots, and I'm going to go ahead and go with the rain cloud plots so that we can see what's happening here. And so what I see here is that the average, I had 16 participants, so n is equal to 16. The average of those numbers that I put in was 67. The standard deviation came down to be 21.90, and the standard error, which would be the standard deviation divided by the square root of n, so the square root of n would be 4. So 21.90 divided by 4 would be 5.475. That's the standard error of my mean. And my t-test is determined by taking this 67 minus this 50 to give me a difference of 17 points over and above what I expected if they were accurate in estimating their driving ability. And I take that 17 and divide by the standard error of estimate, and I get my t value, which is 3.105. It's evaluated with n minus 1 degrees of freedom, that's 15 degrees of freedom, and comes out with a p-value of 0.007, indicating that my type 1, my probability of it making a type 1 error, if I decide to reject the null hypothesis, is only 0.007, which is very small. So we can see that almost all the data points are except for a few, are coming out above the 50. The median value is shown here. My box and whiskers plot almost most of the data points. In fact, 75% of the data points are above the 50th percentile. And here I have a density distribution, kind of a smoothed out density distribution for my data, and it looks fairly normal. And this test actually does assume a normal distribution. And so I can go ahead and click over here for a test of normality. And it shows that does a Shapiro-Wilks test of normality and gives me a probability value. And the probability value is 0.760. And typically we would say that a significant result is less than 0.05. For the test of normality, I would say it should be significant at 0.01. But this is clearly not significantly different from a normal distribution. And that fits with what we're seeing here because we get a curve that looks fairly much like a normal distribution. You can also see this as on QQ plots. So the QQ plot is another way of viewing the assumption of normality. And the QQ plot, I will show you in a later video, actually tells you the same thing as this density distribution in some respects. But it does it in a completely different way, such that if you have a nice normal distribution, these data points should line up on a straight line here. And they are lining up pretty good. Typically when I'm teaching undergraduates, I would say what you're looking for is if you have 15 degrees of freedom and you look up the t value for 0.05 for a two-tailed test, you're going to find 2.131. And beyond that point, beyond a 2.131 on the right-hand side or beyond a minus 2.131 on the negative side, you're going to reject the null hypothesis. We get that 2.131 specifying alpha to be 0.05. Now, if you get a t-value above that, like a 2.5, a 2.5 will actually have its own probability value in the curve. For 2.5, it's going to be approximately 0.015. And just like a 2.5 is greater than 2.131, indicating that we should reject the null hypothesis, a 0.015 is less than 0.05, so this probability value is further down in the curve than where we set the rejection region, and so we should reject the null hypothesis. That's what we're seeing here. This p-value is less than 0.05, and hence we should reject the null hypothesis. If we were, on the other hand, to get a t of, say, 1, if that was the result that would come out, then you would take this whole area under the curve on both sides, since we're doing the two-tailed test, and that would be an area of around 0.32. And so if the p-value here was 0.32, that's not less than 0.05, just as 1 is not greater than 2.131. And so that's another way of judging the significance. So we can tell that we have a statistically significant result simply on the basis here of noting that the p-value is less than 0.05. Now that's a lot to take in, but watch further videos and it will become clear. Thanks.